What we're going to look at is a sequence of alcohols. And actually, let me draw these really quickly on the whiteboard so that you see what they are. So now that we're done with ionic stuff here, what we're going to be looking at are the following molecules. So we've got, let me use the black one here. So we've got propanol, butanol, 1-pentanol, 1-hexanol, 2, 3, 4, 5, 6, 7, 8, there we go, and 1 heptanol. So notice all I'm doing with these molecules here is bit by bit extending the carbon chain, but every one of them has an OH, an alcohol group, at carbon 1. And so they each have one H bonding site. So bear in mind, this is going to mean water's really, really interested in that part of the molecule. On the other hand, the rest of the molecule here, very much nonpolar and getting bigger and bigger and bigger. So the only thing that is going to be able to happen between water and the rest of the molecule is the formation of London forces. Now, what's interesting particularly about the data that we have on this PowerPoint slide is that what you can see is the effect that the increasing amount of carbon has. Namely, that when I start off with ethanol and propanol, which are very small amounts of carbon, and the OH group on the end, I have practically infinite solubility. In other words, I can mix these together in any proportion I like, any amount of ethanol or propanol, any amount of water, and they'll mix together no problem. But once I hit 1-butanol, there's an upper limit. That's what solubility generally means, is how much can I get to dissolve before it stops dissolving. And so butanol sits here at 73 grams per liter. Now that's still a pretty decent amount. Imagine for a moment that you have, a half of a 1 liter bottle of, or of a 2 liter bottle of soda. You can kind of picture that amount of liquid. This is saying that you could fill up your graduated cylinder 3/4 of the way to the top, roughly, with butanol, dump that in, and have it mix perfectly. But any more than that, and you would have a layer of butanol that did not mix. Now, if I want to say that in terms of molarity, that's 1.1 moles per liter of water. Pentanol, notice it drops down to 22, and that is an even more precipitous drop here in the molar solubility because pentanol is heavier. So 22 grams of pentanol is even less molecules than 22 grams of butanol would be. And we keep on trending downward. Hexanol. Now that I've got 6 carbons sitting here on the outside, I can only get 6 grams per 6 grams of hexanol per liter to dissolve, and I'm down to less than a gram when I get to heptanol. And so I think what we can sort of see here is that really, if I want to get these things to dissolve in appreciable quantities, I can't go much further than roughly 4 or 5 carbons per hydrogen bonding group. That's about it. And so what we get here is generally this sort of 4 or 5 to 1 rule. In other words, 5 carbons per hydrogen bonding site. This is going to be kind of the barrier. Right about here, we're usually at marginal, we'll say. Oh boy, I ran out of space. Marginal solubility. Any more carbon than this, and you basically don't dissolve. Any less carbon than this, and you probably dissolve pretty well. And it's worth at this time just kind of reminding ourselves what functional groups are really going to help out with this. If I'm looking for functional groups that will provide hydrogen bonding sites, obviously I'm looking at things that would hydrogen bond themselves, so stuff like carboxylic acids, things like alcohols, things like amines, as long as they're not tertiary, or amides, as long as they've got at least one H on them. But it's also worth recalling for a second that what I might also find that could help out with this are things that might not hydrogen bond with other groups like themselves, but would hydrogen bond with water. Other things that might at least have an acceptor present on them. And so for those, the ones that might have acceptors, we're thinking about stuff like aldehydes and ketones. We're talking about ethers and esters. Anything like these would be able to form hydrogen bonding attractions with water. Now, they might not bring a donor to the table, so they might not be as effective, and we're at least going to be generalizing a bit here, but these are some of the functional groups that will help something dissolve well. By contrast, if I'm thinking about things that are just made up of carbon, we're talking about alkanes, along with alkenes, along with alkynes. We're talking about aromatic rings. Aromatic rings in particular are problematic. Those things are bringing you 6 carbons in one fell swoop. If you don't decorate them with something that's capable of helping out, that's capable of increasing the water solubility, those things are usually going to be pretty oily. They're usually not going to dissolve very well in water. Now, what we're going to go ahead and take a look at now are a couple of molecules that exemplify this. And so we're going to start here, now that we've gotten the sense of this, with something that's, here we go, known as hydrocodone. This you might be familiar with if you've ever heard of Vicodin. This is one of the ingredients to that. Generally, Vicodin is a combination of this and acetaminophen. So what I'd like you to do briefly here is count up the carbons and count up the sites for hydrogen bonding and see if you think this would be very soluble, marginally soluble, or insoluble based on what's there. Pause the video. When you come back, I'll tell you your answer. Okay, now that you've had a chance, note some of the groups we discussed are present here. This is a tertiary amine. This is a ketone. This is an ether. This is another ether. Notice that this also has an awful lot of carbon, including an aromatic ring. It's got 18 carbons in it. So in theory, what it should take is somewhere in the ballpark of 3 to 4 hydrogen bonding groups to get this thing to dissolve even a little. And what we have are 4. We've got the ethers, we've got the ketone, we've got the amine. But notice that every one of these is acceptor only. So it's 4 groups, but it's kind of a weak 4 because nothing's providing a donor. The only things that are providing multiple sites would be these guys here because they could each form hydrogen bonding attractions with 2 donors. The amine over here can only do it with 1 because it only has the 1 lone pair. Hydrocodone on its own would not be a terribly soluble substance. You'd be able to dissolve it a little bit, but it's going to be a challenge to get it into solution. But we have a nice trick up our sleeves when something like this comes around. And I started to point it out because I left this slide in the wrong spot, but so be it. We've got another thing we can do here. If I can take something that used to be able to do hydrogen bonding and turn it into something that can form an ion dipole force, I will be in business, because that is going to be a stronger attraction for the water. You're substituting a partial charge with a full charge. And that is something that it turns out nitrogen can do. We're going to learn right after our next midterm about acid-base behavior. And all you need to know here is that amines are weak bases, which means they can accept H+ from an acid. Because they have a lone pair on them, they can make a new bond. So if I take this thing and I treat it with hydrochloric acid, what I end up with now is a salt, an ionic compound. Notably, an ionic compound with a +1 charge and a -1 charge. And now this whole thing, still with 18 carbons, has 3 spots for hydrogen bonding and an ion, a cation, that it can interact with water with. And as a result, this gets much, much more soluble. If I want to inject this substance, I'm not going to inject it as just straight up hydrocodone. What I'm going to do is inject it as hydrocodone hydrochloride. And if you take a look at a lot of plant-based medicines, a lot of opioids, a lot of pain relievers, they are in the form of large basic molecules. And if they've got too much carbon here, what they'll have to do if they want to administer it in a form that your body can take up easily is they need to put it in its hydrochloride form. So take a good look someday in your medicine cabinet if you have any of these sorts of things, you will see blah, 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 hydrochloride, something along those lines for how it's delivered. Because obviously our body can't take it up if we can't get it to dissolve and go into the bloodstream. Now, we've taken a look so far at molecules where it's an either-or proposition. Either you dissolve or you don't. What we're going to look at in our fourth video are molecules that really straddle this line, not by being marginally soluble, but by having large chunks of them that are very, very interested in water, and large chunks that are very, very not interested in water. And they can do some really important things to us in terms of setting up the inside and the outside of what we are, and helping us clean off the outside of what we are in situations like our shelter in place.